Fill windings are rules which control how a complex path will be filled. These can cause some strange behaviors which may result in some weird rendering. Understanding how fill windings work can help in recognizing these when they occur, and they can be quite easy to fix once you recognize the problem. Here is a compound path which consists of two distinct paths, an inner circle and an outer circle. If we were to fill this compound shape, then we might expect that anything which falls anywhere within the outer point of the path should be filled. But on the other hand, we may want to punch out the inner circle to create a donut shape. These two logical fill models are what we refer to as fill windings. They're the rules by which the renderer determines whether any given pixel on the canvas should be painted with the fill color. To understand how fill windings work, we first need to understand an important thing about how this compound path is constructed. We're not going to go into the actual path data itself, but it is necessary to understand that both of the circles which make up this path are drawn in an anti-clockwise direction. The direction of the paths is key to how one fill winding rule works. The first fill winding that we'll consider is the even-odd rule. To determine whether any given pixel should be colored using the fill color, we draw an imaginary line from that pixel to any edge of the canvas. It really doesn't matter which direction we go, the rule will always evaluate the same way. Let's pick a point somewhere inside the inner circle. We imagine a line from this point to the right edge of the canvas and count the number of times we cross the path. If the number is odd, then it is considered inside the path, but if it is even, then it is considered outside the path, and 0 is considered an even number. So for this point, we'll cross the path twice, so it is outside the path and will not be filled. If we do the same for a point inside the outer circle, but outside the inner circle, we'll cross the path once, so this is inside the path and will be filled. Using the even-odd rule is how we get the fill logic where we punch out the center of the path and get a donut shape. The other fill winding is called non-zero, and this is the default fill winding if none is explicitly set. It works in a similar but slightly different way to even-odd. As before, we imagine a line from any given point to the edge of the canvas. This time, rather than counting the number of times we cross the path, the direction of the path when we cross it is important. If the path we cross is traveling from right to left as we cross it, then we increment the counter. But if it is traveling from left to right, then we decrement the counter. When we reach the edge of the canvas, if the counter is non-zero, then the point is inside the path and should be filled. But if it is 0, it is outside the path and should not be filled. In this case, because the paths are both drawn in the same direction, any point inside the outer path will result in a counter value which is not 0. So we'll get the behavior where anything inside the outer path is filled. However, if we change the direction of one of the paths, then a point within the inner circle crosses two paths in different directions. So we increment as we cross the inner path and decrement as we cross the outer path because it is going in the opposite direction. We get an overall count of 0 and the point is outside the path. A point within the outer circle but outside of the inner circle crosses a single path, so we'll always get a non-zero value, and so this point is inside the path. This change in direction means that we'll now get the same behavior as the even-odd rule. If we turn our attention to a vector drawable, we can specify which fill winding we'll use using the fill type attribute on the path. The preview panel will show this as we change the fill type. In this case, both circles are drawn in the same direction, so specifying a fill type of even-odd results in a shape with a punched out center. But if we change the fill type to non-zero, then we'll get a completely filled shape. This becomes important when you want one of the specific behaviors but aren't getting it. If you require the punch-out behavior of the even-odd fill winding, then it may simply be a case of specifying the correct fill type. However, if you require the fill-all behavior of non-zero, then it may be necessary to reverse the direction of one of the paths and specifying the non-zero fill winding.